Hello everyone, welcome back to Deterministic Optimization. Let's continue our discussion on algebraic aspects of linear optimization. In the last lecture, we studied how to find basic solution in standard form LP. And in this one, we're going to learn how to find basic feasible solution for standard form LP. And let's look at an example first to find basic solution, and then see how do we go from there, from a basic solution to a basic feasible solution. So here is a standard form LP. It has a minimization problem of a linear function here of 3 variables, but the entire problem has 5 variables, okay? So that means there are 0 times x4, 0 times x5 in the objective. And the constraints include 2 linear equality constraints and 5 non-negativity constraints. Those are greater than or equal to 0 constraints for all the variables. And also, as we said earlier, we always assume that our standard form problem has linearly independent equality constraints. You can actually check these 2 constraints here, -1, 1, -1, 1, this, and 0, this vector, versus this -2, 1, 1, 0, -1. These 2 vectors are actually linearly independent. We can write down the matrix form. C is a 5 by 1 vector. A is this matrix here. Remember, we have 5 columns corresponding to 5 variables. Each column corresponds to 1 variable. And as I said earlier, these two rows are linearly independent. You can easily see that because I have a 1, 0, and 0, -1. So these 2 columns are linearly independent. Therefore, the 2 rows also linearly independent. B is right-hand side, which is 2, 3. Okay, let's see how do we find a basic solution for this standard form. Remember, a basic solution comes from 2, in this case, 2 linearly independent columns. So you can find any 2 linearly independent columns that will generate a basic solution. So we can have some freedom to choose which 2 columns that we want to make them bases. So, for example, we can choose the first 2 columns, -1, -2, and 1, 1. And these 2 columns are actually linearly independent. It's easy to see because the determinant -1 minus -2 is 1. So this actually is invertible matrix. Therefore, it must have 2 linearly independent columns and also 2 linearly independent rows. And because these 2 columns are columns 1 and 2, so they correspond to a vector of xb, which is the basic variable of x1 and x2, the first 2 variables. And since b is invertible, it is a basis, while n is the rest. So we have first 2 columns as b, and then the rest columns are n, non-basic variables, x3, x4, x5. And the way to generate the basic solution corresponding to this basis is to set the non-basic variables to be 0. Okay, so this 3, x3, x4, x5 equals 0 gives 3 active constraints, and they are active from non-negativity constraints. So in total, we have 5 equations in 5 variables, 2 from the existing equality constraints, 3 from the new active constraints coming from non-negativity. So let's compute the basic solution. Well, because b is invertible, I can just directly compute the basic variable xb as b inverse times b, and b inverse is very easy to find. We have b here, -1, -2, 1, 1. If you remember from your linear algebra class, to invert a 2 by 2 matrix is actually quite trivial. So the way to do that is you switch the diagonal elements. So you put 1 here and -1 here, and then you negate the off-diagonal elements. So -2 becomes 2, and 1 becomes -1. And then you have to multiply the whole thing by 1 over the determinant, or divide that matrix by 1 over the determinant in this case, the determinant is minus 1 times 1 minus minus 2 times 1 is 1. So we got this inverse, okay? You can review your linear algebra to, or Google online to see a formula that I just described for inverting 2 by 2 matrix. So that is B, and multiply with the right-hand side, lowercase b, 2, 3. We exactly get -1 and 1. Okay, and that's the basic variable part. The non-basic variable part is easy. They're all 0. The non-basic variables of a basic solution are always 0. So when we put together, we have a basic solution, x1, x2, all the way to x5. They're equal to -1, 1, and 0, 0, 0. Okay, so -1, 1, these are the basic variables, and 3 non-basic variables. So why do we have 2 basic variables? Because we have 2 equality constraints to start with. Why do we have 3 non-basic variables? Because we have 5 variables. So if 2 are basic, the rest we set them as non-basic variables. Okay, this is a basic solution by construction. Okay, but the question is this a basic feasible solution? Meaning, is this basic solution feasible? Well, first, to be feasible, it has to satisfy AX equals B. And we know that this one satisfies AX equals B. That's how we construct this solution. And the second constraint is non-negativity. That means every component of this basic solution needs to be non-negative to be feasible and to be a basic feasible solution. And obviously, this -1 is less than 0. So this solution here is a basic solution, but not basic feasible solution. Okay, so you see that the procedure is the following. First, we pick m linearly independent columns from A. In this case, A is 2 has 2 rows, so we pick 2, m equals 2, we pick 2 linearly independent columns to form a basic solution. So from the basic solution, we have to check if every component of the basic solution is non-negative. So if we unfortunately get to a basic solution that is not feasible, we just need to try again, to try another basic basis matrix, meaning pick another 2 linear independent columns from A, form the basic solution, and then see if that basic solution has non-negative components. So let's do that. Let's try another basis matrix as an exercise. Now, this time we pick columns 3 and 4 of the A matrix, and that is -1, 1, 1, and 0. Again, this matrix is easy to invert. The inverse is 0, 1, 1, 1. You can always double check if this is truly the inverse of this matrix by just multiply them. They should be identity matrix. So then this basis matrix gives the basic variables as B inverse B, which is 3, 5. So now you see the basic variables are all non-negative. And the non-basic variable is always non-negative because they're 0. So in other words, to test if a basic solution is basic feasible, you just need to look at the basic variables. They should be non-negative. So this 3, 5, 0, 0, 0, and if you want to put them in the right order, is 0, 0, 3, 5, 0. So this solution is basic feasible solution. Okay, so this is the procedure of finding basic feasible solution. You try a basic solution, construct it, see if all the basic variables are non-negative. If it is, then we're done. We got a basic feasible solution. Otherwise, try another set of bases. Okay, let's quickly summarize. We just learned this procedure to find basic solution. We sample or we pick bases, meaning m linearly independent columns, compute corresponding basic solution, and test non-negativity. Okay, and this procedure, if you're unlucky to start with a basic solution but not feasible, you just need to try another one, and eventually you will find a basic feasible solution. So this is a procedure that you can use to find basic feasible solution, especially for small problems. For large problem later, we'll see that this procedure is not very efficient, but this procedure is for the purpose to understand how to find basic solution, how to find a basic feasible solution, how to compute them. Okay, thank you.